Hello. Let's see. You should see the desktop now and hear me. Is everything still okay?
Yes.
Yeah. Okay, great. Thanks. So let me get things set up. All right. Now let's see. You have a homework assignment due on Tuesday. Does anybody have any question about the homework assignment? Like now would be a good time to, has anybody got a general question or something you want to ask about this homework assignment? Any kind of question about it right now? It's due on Tuesday.
Do you still allow us to work on older assignments to improve them?
Yeah, but yes, but you can't turn them all in at the end of the semester. At some point, I'll have to, like right now, I'll still accept the older assignments, but at some point, I'm gonna grade them, and then after I grade them, I won't accept them anymore because I won't have time to go back and redo them. So I'm hoping to grade them pretty soon, but I'll still accept the older ones, assignments 1, 2, and 3, but I won't be accepting them at the end of the semester because at that point I'll have so much grading to do that I won't have time to go back and redo older assignments. So if you haven't turned in 1, 2, or 3, you should turn them in as soon as possible. Okay. So I'll still accept 1, 2, and 3 at this point. Okay. Okay.
Thank you.
Other questions? Any question about assignment 4, about the other assignments? And if you have questions about assignments 1, 2, or 3, if you're still working on them, you can feel free to send me emails and ask questions about them. So the important thing is to learn the stuff, to figure it out. So if you're still working on one of the previous assignments, you can feel free to ask questions about it. Okay. All right. Now, anybody got any question about homework assignment 4 that's due Tuesday? Okay. Well, we're going to pick up where we left off the other day. Let's see. We were doing these recursive examples, and we wanted to do the next one, which was number 15. So let me download the file, and we're just, these are done for you, and I want to go through one of the tricky ones. Okay, so let me delete the ones we've already done. So delete these. Okay, yeah, the other day we did 11, 12, 13, and 14. We did those. Okay, the next one is flatten. Flatten's a tricky one. So I wanted to do flatten in class because it's kind of, it's one of the, it's a very famous function. The flattened function is in every library. Almost every language has some kind of version of flatten in it. Okay, so the flattened function takes in a list of lists and it flattens it into a single list. So see, it takes 1, 2, 3, and just pulls them out of that list and puts them into this list, and then takes 4, 5, puts them next, then 6, 7, and 8, puts them next, ignores the empty list, then 9 goes at the end. So this is referred to as flattening a list, or well, it's flattening a list of lists. Okay. Okay, so it's another one of the things that comes up in almost every data processing, like libraries for processing data. You quite often have data. These can be thought of as the rows of a table. So a list of lists is often thought of as row 1, row 2, row 3, row 4, row 5 of a table. And flatten can be used to turn a table of rows into one long array. Okay, so flatten is kind of useful. One use for it would be to take a table and turn it into an array. All right, but it's a tricky function to write. It's recursing simultaneously on the outer array outer list, and then it recurses on each inner list. So it recurses on that, then it recurses on that, then it recurses on that one, and that one, and that one, and then it's done. So it's like a nested for loop kind of thing, but it's sort of nested recursion. So it's usually not referred to as nested recursion, but that's kind of how you can think of it. It's almost, it's like it's recursing on this list here and the list inside simultaneously. Okay, so it's actually really tricky to write. It's actually, notice it's just going to end up being 3 lines of code. It's not long. It's not a lot of code, but it's a tricky one to think about if you had to write it yourself. So let's just go through and see how you would think about it. Okay. If you give me an empty list to flatten, there's nothing to do. So I give you back the empty list. Okay. Now, if you didn't give me an empty list to flatten, you gave me a list. If you didn't give me an empty list, you gave me a list that's not empty. So it's a list with at least one list in it. Okay. So you've given me a list with at least one list in it. So there's this list in it, and then there might be some others that I don't care about. Okay. So you haven't given me the empty list. So you've given me a list with one list in it. So now I want to start processing that first list in the list. Okay. Now that list might be empty. You may have actually given me the following. You may have given me a empty list with some stuff after it. Okay. Well, if you gave me an empty list, there's nothing to flatten. Yeah. So I would just go on to the rest of the list. So there's nothing in this thing to flatten. So, okay, now this is here. If you gave me a list where the first thing in the list is the empty list. So that's this case here. You gave me a list, and the first thing in the list is the empty list. There's nothing to flatten in this empty list, so I'm just going to flatten what's left. I'm going to flatten this stuff here. Okay? So if you give me an empty list, there's nothing to flatten. If you give me a non-empty list, the first thing I worry about, okay, it's a list with a list in it, but the list in it is the first list in it is the empty list, and there's nothing to flatten in it. Notice that I don't return an empty list. I just go on and flatten what's left. I flatten the rest of the list. Okay, so the list you gave me is not empty, and what it holds is an empty list in front of the rest of the list. Okay, so I flatten the rest of the list. Okay, now I know you've given me, now I'm to the point where it looks something like this. You've given me a non-empty list, and the first list in the non-empty list is a non-empty list. So I've got a non-empty list where the first item in it is a non-empty list. Okay, so my first case was a completely empty list. In fact, here's what the cases look like. First case was a completely empty list, so I flattened it to just an empty list. Second case was a non-empty list, but the first thing in the non-empty list was an empty list. Now I'm in the general case. I'm a non-empty list. The first thing in the non-empty list is a non-empty list. So what I need to do now, this is the tricky part, X is going to get pulled out. So this is going to go to X is going to get pulled out. And then what's left is I have to flatten this stuff here and then flatten what's left over here. So notice I'll have to flatten what's left. So I'm going to pull out the X, and then I'm going to have a bunch of stuff afterwards. Okay. If you think about it here, the output here was the empty list. And the output here was, well, the flattening of all that other stuff. So I just kind of say it was the flattening. What would go here would be the flattening of everything that came afterwards. Okay, this didn't contribute anything to the flattening. Okay, now this is contributing X. Okay, but then I have to flatten what's in here, and I have to flatten what's out here too. Okay, so what I'm going to do is I'm going to take this stuff. I'm going to write it this way. The X is going to be at the front of the list. Okay. Now what's going to be inside there is going to be this list, what's left of it, comma, what's left here. Okay, think of it. See, what you're going to do is pull this X out and make him the front of the list. Okay. And then what's left is to flatten this. Well, I've pulled the X out here, so I'm flattening the rest of this list. And and then there's still these other lists to process. So it's X in front of flatten what's left of the first list and what's left of the other lists. See, this is what's left of the first list. This is what's left of the list of lists. Okay. So I turn that into code up here as X in front of flatten. Okay. The rest of this list was the X's. See, the X's are these dots here. If you want, I mean, those dots are the X's. I'm showing them as dots. Those are the X's. X in front of what's left. X in front of what's left. This is this set of dots. The other sublists. This is the rest of the first list. This is the rest of the sublists. Okay. So I pull the X out. That's here. I put it at the front of flattening. The rest of the first list put back in front of all the rest of the lists. Okay, so I have to put this guy back in front of all these. This guy here is this list, and I have to put it back in front of all of these. Okay, it's very tricky. Notice it's one of the interesting things about this kind of programming, and believe me, there's lots of this kind of programming going on in the world these days. This is becoming more and more ubiquitous. Instead of writing 50 lines of code that are easy to write, you write 2 lines of very tricky to write code. And there's a well-known phenomena. This has been measured many, many, many times. If you give the same, you take experienced programmers and you give them a kind of serious problem, and you let them write it in Java and write it in a language like ML or Haskell. Okay, so you give them the same problem, and they tell them write it in Java or C++, and then write it in Haskell or ML. The ML and Haskell versions will usually be roughly 50 to 60% shorter than the Java and C++ versions. They almost always come down way shorter. Usually the rough rule of thumb is about 60% shorter. You know, so 100 lines of Java or C++ would probably be 60 or 70 lines of Haskell or less, or of ML. You end up writing less lines of code, but those less code lines are somewhat usually trickier. And that's actually considered a benefit in the long run, because bugs are directly proportional to the number of lines of code. 100 lines of code is going to have more bugs than 60 lines of code. So even if the 60 lines of code are a little bit trickier, after studying this stuff a lot, there's going to be more bugs in 100 lines of easy code than there are in 60 lines of tricky code. Kind of just works out that way. So if you're working with experienced programmers, there'll be as many or more bugs, and there'll be more bugs in 100 lines of simple Java code than there would be in the shorter number of, now 100 lines of ML code would have as many bugs as 100 lines of Java code. The number of bugs is proportional to the lines of code. But if ML can give you fewer lines of code, you're going to end up with probably fewer bugs, and that's pretty much what they measure. But the price is the lines of code themselves tend to be a little bit trickier. The lines of code can be, especially if you're not real used to that, they be like this. Yeah, that's a pretty tricky line of code. Yeah, it's really, yeah, it helps to draw little pictures to help to guide you through this. Okay, so it's now in the case where the first item in the we have a list of lists, and the first list is not empty. So the first list in the list of lists, this is the first list, this is the rest of the list of lists. The first list in the list of lists is not empty. That's the guy that ends up going to the front of this thing. Then you recursively flatten this thing, put back in front of this thing. So you have to put this one back in front of that one. So that's this. You have to put them back into the list of lists and then flatten it. Okay. One line of code, but it's kind of, it takes some real thinking to get that one line of code. Now, here's watching it run. If you then, like, another way to think about this is to think about what it would do with a specific input. Okay, with that input, what it's going to do, it's going to take 1, put it in front of the flatten of 2, 3, and all the rest. Okay, so it pulled the 1, out of here and put it in front, which is what you wanted to do, but it took this kind of tricky code to do that. It pulled the 1 out. Okay, now you're flattening this. So you're going to take the 2 out, cons it onto the flatten of the list with just 3 in it, put back in front of all these lists. Okay, so that's this line of code over. So far we've done that line of code 2 times. Okay, then now you need to flatten this. So you're going to take the 3 out here. That's going to leave you flattening an empty list in front of these sublists. Okay, now you've got a case of this middle pattern. So now we're flattening a non-empty list where the first item in the list is the empty list. Okay, and all we do is drop the empty list. So we get this result now. Okay, that was this middle pattern. See, you just ended up flattening what was left. There was nothing put in the front. Okay, so now we've processed that first sublist. See, now we've managed to process that first sublist. Okay, all right, and then now you're processing this. Now you're flattening this. Okay, so you'll pull the 4 out. That'll leave a list with just 5 in it. Then you'll pull the 5 out. That'll leave another empty list. Okay, so that'll be 2 more iterations of this pattern. And now we're back to that pattern there. We're flattening a list of lists where the first list in the list of lists is the empty list. So we just drop the empty list. Okay, and I didn't continue, I didn't finish this, but you can go on and on and on until you finally hit that pattern there. Now, so it'd be a lot more steps. You have to process this list. Then there's an empty. I purposely put an empty list in there because it's just going to get dropped. And then you have to process that list. Then you finally get to the empty list, and it'll give you back the empty. Eventually, after a lot of steps, you'll get to 1, cons down to 2, cons down to 3, cons down to 4, cons down to 5, cons down to 6, cons down to 7, cons down to 8, cons down to 9, and you'll finally get to that base case where you're consing on to the empty list. You'll get there'll be this one last case where you get to this. You'll only get to this case one time. You'll only get to this one time, and that'll give you this empty list at the end. And then you can put 9 in there, then 8 in front of it, then 7 in front of it, and you'll get the, then you'll get the final answer that's 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay. Actually, in the ML really does it this way. ML really does get up to this, then work its way back to actually, it actually literally does this. If you were to watch what was going on inside, you would literally see it. It kind of, it works its way back out. If I wrote it all out, it actually literally does the following. It has to work its way back out from right to left now. Okay, see, it'll work its way back out. It'll build out to here, then it'll work its way back out. And that is literally what happens inside of if you looked at the code the compiler was spitting out and you were able to watch what was happening as the code was executing, you would see that it really is building up this concatenation of 1 in front of 2 in front of 3 in front of 4, all the way till it gets down to, so there'll be a bunch more steps here. Okay, there'll be a bunch of steps there. Eventually you get to the base case. So you get an empty list here. Then you have to go work your way back up. You have to concatenate these things from right to left until you get to the final answer. So you can go ahead and fit. It's good to think this way. It's worth it to actually think literally of going through one of these processes, because that's actually what it helps to understand and to think and realize it's really doing this. It's really going through all these steps. Okay. And once you get used to that, you start getting better at thinking recursively. I think I'm almost done. Yeah. Okay. There's all the steps. It really does build this out, then collapse it back in. That is literally how the system works. Okay. If you're trying to analyze the running time of this, for example, if you wanted to know like how many steps there were, you would have to realize that there's steps that build up this long string of concatenations, and then there's steps involving bringing it back down to being this list here. Okay. All right. So notice out of these two base cases, this base case, you only hit it once when you get to the very, very end of the list. But this base case, you land on it for every one of these sublists. So you get that base case when you empty this list out. You get that base case when you empty this list out. You get that base case when you empty this list out. You get that base case right away on this one. And you get that base case when you empty this one out. So you hit this base case for each one of the sublists. Okay. So flatten is a famous example. Once you've written flatten, you don't really need to rewrite it again. Flatten is the main tool for working with lists of lists. And a lot of times when you start really using this, if you have to process lists of lists, usually you can do it by making some use of flatten. Quite often, flatten can be your tool for processing lists of lists. Okay. So you don't necessarily have to rewrite this code. If somebody gives you a problem and you think, oh, I can use flatten, it can make it so you don't have to write this code here. You can just maybe use flatten in a clever way and process a list of lists. but it's a really good example for just thinking. Flatten is a good, a good challenging example of recursion on lists. Okay. All right. Now, here's an example of something you could do with flatten. Okay. Like this one's an example of something that you could write yourself, or you could write it with flatten. Write a function that sums up the lengths of the sublist. Okay. So for example, take this guy here. It's got a list of length 3, a list of length 2, a list of length 3, a list of length 0, and a list of length 1. And the answer is, what's the sum of all the sublists? Okay, so that's 3 plus 2 plus 3 plus 0 plus 1 gives you 9. Okay. Now, notice that that's the same thing as if you just flattened this guy and found the length of it. Okay, so if you want to find the sum of the lengths, if you realize, well, that's really, I mean, I've got a list of lists, but what the problem is really asking for is to flatten the list and just take the length of the flattened list. Okay, so you could use flatten to solve this problem. On the other hand, you could solve this problem more hands-on. You could basically say, well, the list is a list of lists, so I want to find the length of this list. Okay, so that's the second one. The second one says, oh, I find the length of this list and add it to the result. Okay, so if you give me an empty list, length is 0. If you give me a non-empty list, I take the length of the first sublist and add it to the recursion on the rest of the sublist. Okay, find the length of the first sublist and add up to the lengths of all the sublists. Okay, that's one step more direct. That's one step into what this thing does. Notice this would be the in a way, this would be the shortest solution. This would be just a little bit longer. On the other hand, you could say, well, I have to count all the items in this list of lists. So if I want the sum of the lengths, I have to count 1, 2, 3, 4, 5, 6, 7, 8, 0, 9. So then I could write it where I mimic what flatten does. And maybe I think this is a good idea, or maybe I don't want it. Maybe I don't want to write it this way. Okay. So what I'm going to do is I'm going to actually write it this way, where I say, well, if you give me an empty list, there's nothing to count. If you give me a non-empty list, but the first item in the non-empty list is an empty list, then I don't count that list. I just drop that list and count the rest. If you give me a list that's non-empty, and the first item in the list is a non-empty list, I don't care what's in that list. 1 plus the sum of the rest of that list in front of all the other sublists. Okay, that mimics what flatten's doing. Okay, so I could write it using flatten, or I could write it really bare bones. And now, there is a difference between this one and this. Okay, imagine a list that's of length, say, 1 billion items long. To flatten the list, you have to traverse the whole list. So you start at the beginning and you walk the whole list, flattening it. Then after you've flattened it, you have to compute the length. Well, you have to go back to the beginning of the list and walk the whole list again to count its length. So this requires you to traverse the list 2 times. Once to flatten it, and once to count how many are in it. Okay. What about this one? Okay. This one, I'm going to go through the list. I'm going to get the first item in the list and just then walk it to count its length. But then I recurse on the rest of the list. I don't ever walk this list again. See, I'll pull that first list out, walk those items, and then go on to the rest. That sounds twice as fast as this, because I'm only going to touch every element one time. I walk this list once to count it, then add it on to, well, recurse on the rest of the list. Okay, so that sounds pretty good. Here, remember, I had to walk the whole list to get a flattened version of it. Then I had to walk the whole flattened list to count them. So, okay, whereas this one, it looks like, well, I walk that sub list once, get its length, add it on to process the rest. So I'm only touching each item in the list one time. So if the whole list has 1 billion items in it, I only touch each item one time, whereas this one touches each item 2 times. What about this one? Okay. This one pretty much is exactly this is like the middle one. Okay. If you give me an empty list, I get 0. If you give me an empty list in front of a non-empty, if you give me a non-empty list with an empty list at the front, I just kind of drop it. I just drop it and go on to the rest. If you give me one item in a list, I count that item, and then I keep working on the rest. Okay, but I only touch that one. Each item only gets touched one time. I pull it out of this sub list, count it, then work on the rest. So again, I only step through the list one time here. So if you look at this, this is probably really the best solution right here. It's not as short a piece of code as that is. It's shorter than that. This one is better than this one because it's easier to read. But this one is a little bit better than this one because it's probably about twice as fast. It's probably close to twice as fast. It's not going to be exactly twice as fast, but it's going to be kind of close to it. Okay. So this one might be your best choice because it's relatively straightforward to read and it's probably going to be faster. Now this one has the advantage of being really short, so it's easy to read. Okay, so if you're counting lines of code, this is 1 line instead of 2 lines. Okay, so you might think that that's better. And there's actually the difference between these two is actually people will argue over that. Some people would prefer that one because it's really direct. It's 1 line of code. You know what flatten does, you know what length does. So there's not much chance of that being wrong. Flatten the list, and then take its length. This one's already kind of a little bit tricky code. There's a lot going on. You're pulling something out of a list of lists, computing the length, then adding it to some recursion. Notice that there's no recursion over here. This is not a recursive function. It's just the length of the flatten of list of lists. So there's not even recursion. The recursion's buried in this and in this, but it's not written as a recursive function. This one is written as a recursive function, so it's a little bit more complicated. Some people would say this one's better. Who cares if it takes a little bit longer to run? With a really, really, really good compiler, some of the modern compilers can actually take this and figure out that it's this. Some of the modern compilers are amazingly clever at what they can figure out. And a lot of times programmers are told, write the clear code and let the compiler figure it out for you. And the compiler theorist's job is to make the compilers get better and better. And I'm actually pretty sure that a modern compiler can take this and turn it into this. It can see that what's going on is this thing here. And so it probably wouldn't even end up traversing the list 2 times. It can probably figure out that it might need to do this. There's a lot of research going on these days in writing better and better optimizing compilers. This one, probably nobody would really want you to do this. There's no reason to write this thing out that bare bone. Essentially here you're mimicking what Flatten does. This is really written to look like Flatten, but this one here in the middle is a good compromise. If you are worried about efficiency, that one's going to be the most efficient one. It's going to only traverse the list once, and it's not much worse in writing than that one there. Okay, but this is nice because it doesn't even need recursion. You just compute the length of the flatten. Okay. And here's another one that's similar. What if you were supposed to add up all those numbers? So you have a list of lists of numbers and you want to add them all up. Okay. Well, you could flatten the list first and then sum up the list. Okay. That would be, because once it's flattened, you can, sum takes in a list of numbers and adds them all up. Flatten takes the list of lists and makes it one list, so you could just sum up the flattened list. Okay, so that's nice, but this will traverse the list 2 times. Traverse it once to flatten it, and traverse it a second time to do the summing. Then you could do exactly like what we did in the middle case here. You could pull out the first sublist, sum just that, and add it on to the sum of what's left in the sublist. That's a compromise between writing code that looks just like flatten and writing something that's as efficient as efficient. See, this will only traverse the list 1 time. It'll pull out the first sublist, walk it to add it all up, then go on to the next sublist. It won't need to go back to the beginning. Okay, whereas that's what this one does. This one, after it's flattened the list, it has to go back to the beginning of the list and start adding them up. Okay, so it has to, at least nominally, if the compiler doesn't optimize it, it has to flatten the list, then go back to the beginning and sum it up. If the compiler is real clever, the compiler might realize, wow, as I'm flattening, I could be adding up the numbers, which is essentially what this thing does. Or it's actually essentially what this thing does. The compiler might realize that I'm going to be adding up these numbers as I flatten them, so it could just go through the list 1 time and add as it flattens. But that would take a real clever compiler. But I think the modern compilers are getting that clever. I think they are at this point. But if you were worried about the efficiency, you could write it this way, which is still pretty straightforward. That goes through the list once. And then if you wanted to really be sure you go through the list once, you could write it like flatten, but there's probably no real good reason to write it that way. This would be probably the optimal way to write it. It's optimal in terms of speed, and it's optimal in terms of complexity. It's no more complicated than it needs to be. Whereas, okay, you can say this one's written more complicated than it needs to be. Now, flatten can't be written any better than the way that it's written. If you go back up here to flatten, there's no short way to write flatten. There's no shorter way to write flatten. It has to walk through. Now, it only traverses the list 1 time, and you need to traverse the list 1 time, pulling out item after item after item. So flatten traverses the list 1 time, and there's no easier way to write it. These other functions, they could be written in terms of flatten, or they could, work their way through the list, not quite using flatten, but just pulling out sublists at a time and working on sublists at a time, or write it like flatten. Okay, so there's a couple of examples where you can see how flatten would get used to implement something else. Okay, all right. Now let's go ahead and start. So let's leave behind these recursive examples, and let's start talking about what's in chapter 9 in the book. Okay, chapter 9 is chapter 9 is real short, but it's not real brief. There's actually a fair number of ideas in chapter 9. It's not a simple chapter. So let's I got some examples here to look at. There's a number of topics in the chapter. If you look at the slides for the chapter, there's really 3 topics here. Okay, another way of doing pattern matching. This idea here, function values and anonymous functions, that's 2 pages in the book, and it's really a deep idea. I'm not sure if the author, it's a much deeper idea than he leads you to think, and it might be that, I'm not sure why, if maybe he just didn't want to spend much time talking about it, but we'll spend a little bit more time, because I think, especially when you want to get to higher order functions, it helps to have spent a fair amount of time thinking about this. Okay. Oh, and actually, there's really 4 topics. Currying is an example of a higher order function, but it's another very deep idea. So it really should be its own topic. So a little bit more about pattern matching, function values and anonymous functions, which is not a trivial matter, higher order functions, then currying. Currying really should be thought of as its own idea. And then this is just some examples of higher order functions. So this is really just more of this. It's not really a new idea. It's just examples of higher order functions. So there's 4 ideas: the new kind of pattern matching, function values and anonymous functions, higher order functions, and currying. And these 3 things, function values and anonymous functions, higher order functions, and currying, these 3 things are pretty deep. They're not trivial. Okay. The more pattern matching is pretty straightforward. I'll show you in a minute. That's just syntax. So this is a new form, a new kind of syntax. So it's not a deep idea. It's just a new syntax. These are really, really big ideas. And then here it's just he's going to use the idea. These are examples. Some of the predefined examples in the some of the predefined higher order functions in the ML library. Very important examples though. These are really important examples. Okay. All right. So let's start by looking at this extra syntax. Let me think. No, first I'm going to do it in the other way. Instead of doing the extra syntax, it makes more sense if we do these first, because the syntax is related to these things called function values. So I think he's got the order a little bit mixed up. The new syntax really is based on this idea here. So I think we should do this first and then look at the new syntax. Otherwise, you're kind of putting the cart before the horse, because the syntax is about these function values. Okay, so here's an idea. Let me open an example. I'll put this code's not up on the website yet. I'll put it up on the website after class. Okay. Here's what we're used to. F is a function that takes in x and gives us back x times x. That's the squaring function. Okay. And g is the cubing function. Okay. And if I'm going to just copy and paste these into ML one at a time. I mean, I could load the whole file into ML, but I think it's more instructive if I just do them one at a time. Okay, so there's a function. What did I do wrong? I didn't copy and paste it very well. Okay, so I've got this function. Notice the type is int to int. Okay, remember, multiplication can either multiply 2 ints or multiply 2 reals. If you don't tell it otherwise, it defaults to 2 ints. Okay, and since I didn't say otherwise, I get int times int. Okay, and then here's my other function, and its type is going to also be from int to int. Now notice that what it's saying, that when it reports the type, it says f is a function from int to int. Okay, so f is a function from integer ins to integer outs. Notice that it uses the little fn to mean that it's of type function. Turns out that fn is also something you can write yourself in Java, in ML. We've been defining functions using fun. You can also define functions using fn. Okay, that's this next 2 lines of code. Like, look at this. This is actually a line of code of ML. Notice it's not quite the same as this type information. Okay, so what I write is fnx. Here was written f equals fn colon. The colon is type of. F is a function type of int to int. So colon in ML means type of. So f is a function of type into int. F is a function of, g is a function of type into int. Now here I'm using fn in a different way. Here I'm using it as a piece of code. A function that takes in x and gives me out x squared. The arrow here is saying that this is the input and this is the output. So this is a rule, a function rule. And notice it tells me that it's a function of type int to int. There's something missing here. I didn't give the function a name. I just defined what we call a function value. Notice that, like, suppose I do this. There's an integer value. It's a value of type integer. I didn't give it a name. If I want to use it again, I have to type it in again. If I want to add it to 4, I have to type it in again. If I want to add it to, if I have a val x is 3, and I want to add 345 to x, I have to type it in again, right? It's a literal. It's an integer literal. Now, if I do val y equals 345, now it's got a name. So now I can talk about x plus y. Okay, I can talk about 44 plus y. Okay, that's an integer literal. Here I gave that integer literal a name. Okay, now that might seem like I'm really being nitpicky and silly, but now I'm going to do the same thing, but with a deeper idea. This is a function literal. It doesn't have a name. I can't really use it. I can use it. Remember how I could take the integer literal and add it to something? I can take the function literal and use it. Like here. Here's the function. Oops. Here's the function literal. I'm going to apply it to the number 7. Remember? So remember, you give the function and then you give it its input. See, 49. I called the function on 7. That's the function literal. It's a lot like using 345 and adding it to x. I use it literally as what it is. Here I'm going to use that function literal applied to 12. Okay, 12. Now, what happened was 12 was this function is the function. It takes whatever its input is and squares it. Then I said here, apply that function to 12. So 12 was put into x. 12 times 12 is 144. Now, constantly typing the function as a literal is a nuisance. So let me give it a name. Well, how do you give things names? You use the val command. So I'm going to say val f equals the function literal x, f of x goes to x times x. Now I gave that function literal a name. So now I can say f of 12 is, okay. No, real important. This line of code and this line of code are the exact same thing. This line of code used the function literal right there and applied it to 12. This line of code said, well, look up f. The value of f is that function literal and apply it to 12. Okay. That's a little bit different than what I did up here at the top. At the top here, I said, I want the function f of x to be x squared. This symbol, this syntax here is actually a compact version of this syntax down here. Okay, so let me write that down here. The following are equivalent. Function f of x is x times x is the same thing as saying the variable f is a name for the function literal that takes in an x and gives me out x times x. This is just shorthand for that. This is a function literal, and this is giving it a name. And this is just saying, give a name to the function that takes in x and gives you out x squared. Notice you use an equal sign instead of an arrow. This is just a more compact notation for this. Okay. In fact, the compiler converts this into this. This doesn't really exist in the ML language. This line here is the first step the compiler does is it translates that into this. And then it compiles this. It doesn't actually compile this thing. It translates it into this and then compiles this. F is the name of a function. What function is the name of? The function that takes in x and gives me out x squared, which is written this way here. The function that takes in x and gives me out x squared. Okay? So this is a new kind of this is a new idea, function values. Okay. Java doesn't have this idea, and C++ doesn't have this idea. And C doesn't have this idea. You can't have functions that are just sitting there by themselves. You can, in modern Java, you have something very close to this. We'll in a little while I'll show you what the equivalent to this, well, the closest equivalent to this is in Java. Java's has something that's very close to this, but it's not quite exactly this idea here. Okay. Now, this idea comes out of math somewhat also. Like in math, let me show you something. Here's one way to think about this in math. You're used to thinking of this as being the equation of a line. Okay, so you think of that as a function, but that's not a function. That's an expression. It isn't a function. Now here's how I make it into a function. If I write this, that's not the equation of a line. Why is that not the equation of a line? I took this thing and I made it into a function. But I'm not writing the function for a line. Why not? Why would this not be a function for a line? How many variables are in the function for a line? How many independent variables are in this? If you graph it, how do you graph it? See? You graph it with one independent variable. See? It's a graph of one variable. Okay? But what did I define here?
3 variables.
It's a function of 3 variables. So this would be in calculus something you took partial derivatives of, not derivatives. The function for a line would look like this. These are not the same thing. Okay. This says I have a function of 3 variables. So that means I have 3 independent variables. I would graph this in 4-dimensional space, because it would have 3 independent variables, the m, the x, and the b, and then it would have the output variable like z. So this would be like z equals mx plus b, but it's got 3 independent variables. This is what you usually mean when you want a line. But then what's m? Where does m come from? See, m here was one of the independent variables. So I could say f of 4, 5, 6 is 5 times 4 plus 6. See, because the x is 4, the 5 is m, the 6 is b. Okay. Now, what happens when I say f of 4 here? What do? I get m times 4 plus b. What about the m and the b? What did I do over here in Google?
You gave M and B some value.
Yeah, because what if I do this? Is Google going to graph it? Why did it graph one but not the other? Graph that. Why is Google an idiot? Does Google know? Is Google not smart to know that mx plus b is a line? Why did it not graph that? Why did it graph that? That's a line, right? Mx plus b. Everybody who's gone through high school can recite that mx plus b is a line. But why didn't Google draw a line? What stopped Google from drawing a line here? It gave you a bunch of pictures. Yeah, it knows it's got something to do with slope and intercept because it found the right pictures. But why didn't it draw a pic? What's the difference between that and this? What's going, here, where do the M and the B come from? How are you supposed to think of something like that? If it's a programming language, what are M and B here? Like, okay, suppose I write this in Java. I would write int, public static int f int x return m times x plus b. That's valid Java. It'll compile. Well, if I spell it right. Probably want to make these double. How do I make this compile? How do I make sense of this? How do I make this compile?
Define M and B as literals.
Yeah, well, no, not as literals. I need to define them as what? I don't define them as literals. Literal just means, a literal is a number. I don't define a variable to be a literal, but what do I need to do? How do I make this compile? Interview question. Believe me, you will get this stuff. People will quiz you endlessly and mercilessly. They will ask you this stuff. So, I'm asking these questions because I know that you're going to get them and people are going to really push you hard. The job market's kind of competitive. They want to find out if you can think on your feet, that you can solve little problems. These are not hard problems. They're asking you, are you comfortable with the basics of these languages? What makes this compilable?
You have to define M and B as constants.
Yes, you have to and that's what's going to happen over here. Over here, you have to say M is 3, B is 5. Here you'd have to say something like public static int or double M equals 3.0 public static double. Notice that Java is very verbose language. You have to type a lot. Okay. We have a name for this. M and B are non-local references. They're not local. Now, in Java, how do I write that? See, here, my function was mx plus b. That was the parameter, like here. That makes these guys non-local references. This refers to the local variable. So these are non-local references. And in Java, you fill them in with global variables. How do I write this thing in Java? What's the difference between this and this if I write them in Java? What would I write down here to do this one? What would I write down here? So, the idea is that this thing by itself is not a function. It's really what we call an expression. So this is an expression. It tells you how to do a calculation. M times X plus B. By itself, it's saying how to do a calculation. It doesn't say where M, X, and B come from. So it's not a function, it's an expression. I use that expression to define a function of one variable. So the X comes from the function, but the M and the B have to come from somewhere else. See, the M and the B have to be defined somewhere else, and then I can call the function. Okay, now I can do that in Java this way. There's the function with that expression with X as the input variable. How do I get this guy in Java?
You need to create a function that accepts 3 doubles.
Yeah, exactly. Now I would write, I'll just copy and paste this and make a little change in it. It would be double X, double M, double B. I don't change any now, but now M, they're all local variables. Same expression, completely different function. Now it's a function of 3 variables. It's not a line anymore. Its graph would be something much more complicated. Okay, so this expression can be turned into that function, can be turned into that function. I can even turn it into some other functions. I can write f of mx equals mx plus b. That means that b has to be defined beforehand. So, and then in Java, I can do this one. Okay, this would be like that. Now, B is a non-local reference, and I need to define it outside. Okay. Okay. Notice that that's a function of 2 variables, which is not the same thing as a function of 3 variables, which is not the same thing as a function of 1 variable, but they all have the same expression. So the expression is not the function. What does it make it into a function? You have to tell me what the inputs are. So another example would be if I give you this expression. you have no idea what that might be as a function. See, I can take that expression and make a whole lot of functions out of it. F of x equals x times y plus z. Notice that this is really just saying mx plus b. Notice I'm using the same form, but I gave them different letters. Okay, but it's still by itself just means give me three numbers, I multiply two of them and add the third one. Okay, I can then do f of, say, x comma y equals x times y plus z. I can do f of x comma y comma z equals x times y plus z. Now here, let me show you a subtle thing. No, not that one. Yeah. I can do f of x z equals x times y plus z. Here's the subtle one. I should give these numbers so we can refer to them. F4 and 5 aren't the same thing. F4 is a function of x and z. F5 is a function of x and z. They have the same formula on the right, but they're not the same function. This is a tricky little question. Can anybody show me, can anybody prove that F4 and F5 aren't the same? F4 and F5 aren't the same thing. Well, first of all, let's go back. What do I need to do to turn these things into legitimate functions? There's a little bit of a problem in each one. For example, in F1, what do I need to do to make it a legitimate function?
You have to define y and z.
Yeah, because they're what we call the free variables. Another way to put here I call them non-local references. In mathematics, they tend to be called free. We would say that y and z are free variables. Okay. So non-local references are more of a programmer's idea. Free variables is a math idea, but programmers often refer to them as free variables too. The z and the y are free variables, so I better give them values. So up here I can say, well, y is 4 and z is 6. Okay, so I needed to give them values. Okay. In this one, z is a free variable. So to make it a legitimate function, I ought to give you a value, say, for z. Okay. Now here, there's no free variables. Notice that's important. This one, there are no free variables. That's a well-defined function all by itself. Okay. Now here, y is the free variable. So I'll say, say y is 2. And here, y is free. And I'll stick with y. I'll just stick with y equals 2. Now, why are F4 and F5 different?
You'd get different results if you took F4 of say like 2, 3 and F5, 2, 3.
Right, exactly. Let's just plug in some numbers. Plug in 2, 3 here. Plug in 2, 3 here. And let's see what we get out. Okay. In F4, we get out 2 times 2 plus 3. And in this one, we get, in F5, be real careful. Z is 2. Okay, so that's going to be plus 2 over here. And x is 3. So that's going to be 3 times 2 plus 2. Okay. So this one gives us what? 7. And this one gives us 8, right? They're not the same function. Same formula, same expression here, same variables here, but what? Somebody asks you what's the difference, what do you tell them? What's the pertinent difference between F4 and F5?
The order of the parameters.
Yeah, the order of the parameters matters a lot because you match the formal parameters, you match the arguments against the formal parameters from left to right. So you match that to that, and you match that to that. These are called arguments. These are called formal parameters. They are parameters. These are arguments. These are parameters. These are arguments. These are parameters. And you match them from left to right. Okay, so you end up with different results. Okay, so what we're seeing is that a function's got a bunch of pieces to it. There's the body of the function, and then there's the parameters. Now, in all of this, what's actually not very important is the name of the function. Like, let me take all of these and do the following. Let me turn them into what we were doing in ML, anonymous functions. All I do is to do the following. And I'll just put a little arrow over here. And I basically have ML syntax for anonymous functions. See, now these guys, they say, each one of them says, when you give me the parameter x, I'll compute x times y plus z, where these guys are defined up here. When you give me an x and a y parameter, I'll compute that. If you give me an xyz parameter, I'll compute that. So these are the anonymous versions of F1, F2, F3, and F4. The names are not really crucial to this. From the mathematical point of view, all of these things, well, let me just save it. Down here, I have a problem. Can anybody see what the problem is? Last question. Down here, this doesn't make sense down here. Does anybody see what I need to do to fix this? What's the problem when I went from here to here? Now, these were outputs. Seriously, what's wrong? What did I plug 2, 3 into?
You don't know what function you're.
Yeah, so I fixed that by copying the function. I have to copy just like we did in ML. Remember, we could apply the anonymous function directly. So what I need to do is take this, go down here and say, that's the anonymous function I'm using on that input. On the other hand, see, I'm got to make sure I don't get lost here. I'm using first this one, and then I'm using this one. Okay. This function is what we originally called F4, and this one's what we originally called F5, but they don't have names anymore. There's the anonymous function, there's the other anonymous function. When I want to apply them to 2, 3, I need to do that. Okay. Right. So I have y is 2, and then I apply these anonymous functions, and I get these results. Okay, and y is the non-local reference here. That's the free variable. Y is the free variable, so I give it a value up here. Okay, the names aren't crucial to this. So this is what the book refers to. If we go back to the anonymous functions, this is what we've been talking about. Notice it's a deep idea. I don't think this is a trivial idea at all. I think this takes a lot of explaining, a lot of talking about. The book just kind of mentions it in one paragraph. And to me, it's way more complicated than one paragraph. What we're talking about are these anonymous functions. And what's important is to see how an expression by itself is not a function. You can tie an expression to a notation that turns it into a function, and then you, what we call, bind variables to parameters. But this expression can be made into an anonymous function or a named function lots of different ways. The name is not really the key. The key is the binding from independent variable to the expression. The really important part is you take this expression and you say, which one of them are the inputs as a function? So you can take that expression and say x is the input. Or you can take that expression and say that x, m, and b are all the inputs. Or you can take that expression and say that m and x are the inputs. And then you could do that in Java. Notice you get different Java. And then you can go and say, but the name is not really the important part. The name's not important. What's important is telling me what's independent and what's free. What's independent and what's free in the expression. Separate the independent variables and give them an order and say how they're used in the expression. When you do that, when you just talk about the independent variables and the expression, that's called an anonymous function. It tells you what to do, it just doesn't give it a name. If you want to use it, you have to type the literal. There's the function I'm applying to 2, 3. There's the function I'm applying to 2, 3. And those are two different functions. They're, because they have the different order of the variables, they're slightly different functions. Okay. So this builds up the whole idea of anonymous functions. And it brings up the idea of free variables and non-free variables. In this formula, x is that parameter. Z is that parameter. So that x is that first input. X is bound to that first input. Z is bound to that second input. And then I compute. The y is free. I better find a value for y outside my function. If I don't find a value for y outside my function, I get a compiler error. Or ML will give me a runtime error. I'll get an error if I don't have that variable defined outside of the function. I'll get an error. Okay, so the function values and anonymous functions is a really tricky idea. There's a lot to think about there. And it's related very much to what you've seen in math. It all comes out of math, but it's also very much a part of programming. This function and this function in Java are not the same function, even though they look like they're returning the same formula. Okay, you can't look at that and tell me what that function does. You have to look up here and see what are the free variables and the parameter variables. You can't look at just that. You got to look up here too, because it makes a difference. And then if something is free down here, you better define it outside, or otherwise your program won't compile. Okay. All right. So when we come back next week, we'll say a little bit more about these and then see how they relate to these higher order functions. Okay. This is really subtle stuff, and it has a lot to do with, this lets you start talking about programming in a more sophisticated way. At this point, you're going to start using the language of programming and thinking about programming in a more nuanced way, where you actually really see how subtle these things are, the difference between expression and function, and how you can bind or variables or leave them free. So when we start using words now, free variables, bound variables, and then we can talk about the function by itself without a name. and we'll see how where you can make really good use of that in programming. Anonymous functions are very useful, actually. Okay, so we should quit there. We run out of time. Okay, so we'll keep on doing these examples on Tuesday. And if you have questions about the homework, please send me an email if you have questions about the programming assignment. Okay, so I'll quit there. Have a nice weekend. Bye.